Okay, hello everyone. It's 11 here in Colorado, and thanks for coming at the 2023 Econ Seminar Series, and thanks to the people online for tuning in. It's an honor and a pleasure for me today to introduce Dr. Pepijn Veefkind. Pepijn is a senior scientist at the Royal Netherlands Meteorological Institute, KNMI, and an expert in the field of satellite remote sensing of atmospheric trace gases, aerosols, and clouds. He studied physics and meteorology at Utrecht University and conducted his PhD research at the Netherlands Organization for Applied Scientific Research. Pepijn is the principal investigation of the TROOTROPOMI satellite instrument on board of the European Sentinel-5 precursor satellite that was launched in 2017. TROOTROPOMI is Dutch-built and is the most advanced instrument of its kind. And he's also the deputy principal investigator of the OMI instrument on board of the NASA EOS-ORA satellite launched in 2004, and mission scientist for the Tango mission, a Dutch CubeSat mission initiative. He's a member of the COM2M mission advisory group and has served in the European Space Agency's Committee of the European Science Foundation. Pepijn is leading the OMI TROOTROPOMI group at KNMI and is also affiliated to the Delft University of Technology. And today he's going to speak about the role of satellite observation of the atmospheric composition for policy making. Before starting, I would like to remind the people following online that they can type at any time during the talk their question in the field below the video, and I will read the questions to Pepijn at the end of the talk. And with that, I leave the floor to Pepijn. Thank you.
So good morning, everybody. I'm visiting this week and next week here at NCAR ECOM, and I'm very pleased to be here. And I hope to meet a lot of you during this visit and discuss more about the science that can be do with the data that we generate. So today I'm going to talk about what we contribute to policy making with our data and with our insights from our satellites. But before going into the core of the presentation, I would like to say something about where I come from. So as already was said in the introduction, I'm from the Netherlands, from KNMI. It's the Met Office in the Netherlands. It was founded in 1854 in Utrecht. Currently we are close to Utrecht in the center of the country. We provide operational tasks, but also the National Research Center for Climate and Meteorology. And I'm from the R&D Satellite Observations Group, which is about 50 people at this moment. And our focus is on atmospheric composition, atmospheric dynamics, and clouds, aerosols, and space weather. So the group is split in these kind of subgroups. The atmospheric composition is the largest in our R&D group. So when I go somewhere, of course, I look into the TROOTROPOMI data where I'm actually going. And so I did also this time. So here you see a map of the NO2. So this is an annual average of last year, 2022. And you can see all the major cities around the US. But also you can see a lot of detail when you zoom into these kind of images that we generate. So of course I did this also for the Denver-Boulder region, which you see here. You can see, of course, the major, the highest concentrations over Denver. But also you can see how the concentrations are high along the highways, for example. And of course, for all people living in Boulder, they know that the mountains are the best place to be, as you can see here, because the air is really clean there, of course. So today I'm going to talk about the atmospheric composition and how it's changed and how policies are put in place to try to overcome some certain environmental problems. So here you see a schematic of the atmospheric composition. So the atmospheric composition is of course governed by what we put in, so the emissions, the transport, the chemical conversions in the atmosphere, and the deposition back to the surface. Now, as human beings, we are changing the atmospheric composition in many ways by putting in increasing concentrations of gases that were already in the atmosphere, like CO2 or methane, or we put new substances in, for example, the CFCs that affect the ozone layer. And due to that, we have on both the local scale with gases and species that are short-lived, as well as on the global scale, we have changed the composition of the atmosphere, leading to a whole range of problems. And here are the main problems that are caused by changing our atmospheric composition. So, of course, it's the ozone layer through the CFCs, climate change, probably the biggest challenge of our generation and the generations to come. Reduced air quality in the cities and the larger megacities, and of course changes in biodiversity. So what do satellites contribute to this? Well, first of all, they give a great global view of these things, and this is a movie where you see NO2 measured from TROOTROPOMI. This is a composition of many years of data. And you see where the concentrations are highest is where, of course, the population lives, the larger populations. But also you can see, for example, the ship tracks over the oceans. For example, here in Asia, and this is where the big container ships go over the oceans and transport the goods from Asia to, for example, Europe. And I always find this a fascinating movie because when there would be no humans on the planet, this movie would be very boring because it would be blue, almost completely, with every now and then maybe a spike of a natural wildfire that is ignited. So yes, this is directly, you can see here how we are changing the atmospheric composition. Now, how do our measurements from space contribute to policy making? Well, when you look at the policy cycle, everything starts, of course, with the discovery of something. For example, the discovering how CFCs affected the ozone layer, how it destroyed ozone. Then we go into this policy cycle where you have the strategic thinking, you have the development of the policy, you have the implementation of the policy and the maintenance of the policy, and then you go around this circle again. Now there are several parts of this cycle where we actually contribute, and the first one is the strategic thinking, because this is where, for example, agenda setting takes place, where we have to understand what can be done, what measures can be effective to have an effective policy. And that's also important where we show to the policymakers, but also to the larger audience, what the problem is. And then also in the maintenance of the policy is very important. This is where monitoring takes place. So you have to show, is the policy effective? Do we have to do more, or is it good as it is? So these are places where we contribute as a community, and also our satellite data contributes. Now this might sound very abstract and vague, so I would like to go to a very concrete example. So here you see two maps of the Netherlands. So where I come from, so it's a small country. From south to north, it's about 300 kilometers. There are about 17 million people living in this small place of the small part of the world. And here you see two satellite images. One is from TROOTROPOMI, it's NO2. So this is what comes from combustion. So this will be highest where the larger communities, where the industry and the people live. The other one is Chris ammonia. This is through agriculture, especially very intensive agriculture and cattle. So you see here on a small place of the world our nitrogen problem, because in the end what happens, we have a problem with reactive and the deposition of it in nature areas, causing reduced biodiversity. So what the government wants to do is they want to reduce this, and especially want to reduce the amount of ammonia that we emit. And this has led to great protest of farmers, because this means that there should be less cattle, affecting, of course, their income in the end. And these images, they have been used a lot in the public debate about active nitrogen. They have been used, but also misused, because sometimes in the social media, only one of these images was shown and said, well, the other ones are the big problems. It's not us. So you see that with these images, we directly contribute to these discussions, and it's the power of the visual image also that is very important for these satellite data. So I'd like to add a third image here. So that we had regional elections in this year, and this is the percentage of votes that went to one of the parties, the BBB. It's the Farmers' Party, basically. And when you look at this, the ammonia and the election maps, you see immediately the spatial correlation between the two images, and that's of course striking, but it's not so surprising, because these are of course the regions where farming is very important economically, and so it's not that strange that these regions will also vote for this particular party. But it's, I think, a way to show how our data that we normally do in the scientific arena is really important also in the society. So I talked about one of the policies, but of course there are more that we can contribute. So here are a list of policies. This is kind of European-based, I think, apart from the ozone layer, the Montreal Protocol. In Europe, we have the European directives for air quality. For climate change, we have the Paris Agreement and the Methane Pledge. And then for nature and biodiversity, again, EU directives, where also this discussion around nitrogen that I just talked about comes from. So how do we address, and one of the examples here to show is this is NO2 from OMI in 2005 and 2022. And you see the huge reductions that have been taking place. So these reductions are like 30 to 50% in Europe. I think it's the same kind of numbers here in the US. And these are very good images because they immediately show that the policy that was put in place is really effective. So I think, and that's very important because a lot of people don't realize that some policies really are effective in the end. And I think for air quality, for most of the things that we've done in Europe as well as in the US, policies have been quite a big success. So what do we do in Europe on atmospheric monitoring? We have a very large Earth observation program. It's called Copernicus. You may have heard of it. It consists of several topics, and atmosphere is just one of them. For example, ocean is one of the other ones. And for the atmospheric monitoring, we have put into place a system that consists of a modeling and data assimilation part. It's called CAMS, the Copernicus Atmospheric Monitoring Service. And this is a very large project that is led by ECMWF, so the European Weather Center. And then to feed this system, we have satellite observations as well as ground-based observations. As part of the Copernicus system, we have a set of satellites. They are called the Sentinels. So the Sentinels satellite series, they're really part of this larger Copernicus Atmosphere Monitoring Service. And in the bottom, you see some examples of what comes out of this service. So we have forecast data on the global scale, but also on the regional scale over Europe. And we also look at methane anomalies, for example, for climate change, for climate monitoring. And KNMI, we contribute at several places to this whole system. Our modeling department, they contribute to the development of the chemical modeling within CAMS, the global model. We contribute to the validation of the products that come out of CAMS. And of course, we contribute to the satellite observations, for example, with TROOTROPOMI and follow-on missions. So to have a look at the European Earth observation missions. So we have 3 big programs in Europe for Earth observation. You can see it in the bottom. We have the science missions that are governed by ESA. Then we have the Copernicus missions, and we have the meteorological missions. And within with the yellow highlighted circles, I indicate which one contributes to atmospheric composition and atmospheric composition monitoring. And when you look at the current missions, it's METOP-C, or the METOP series, which carry the GOM-2 instruments as well as the ESA instruments, as well as, of course, TROOTROPOMI on Sentinel-5 precursor that's currently active. And when you look at the coming years, so around 2025, you see that there will be quite some new missions. We will have the Sentinel-4 instrument on the geostationary image platform, the MTG sounder platform. We will have the C2M missions. I'll talk about it in a minute. We'll have Altius, which is a LIMP instrument looking at the stratosphere. And we will have the follow-on of TROOTROPOMI, which is called Sentinel-5. So there's quite some missions to come in the coming years. On top of this, there are some other missions that have not been approved yet, but we hope we will also add to these satellite missions. So looking in some detail on these missions. So in the top, these are the missions that have been improved and we are currently developing. So there's the Sentinel-4 mission. As I said, it's similar as the TEMPO mission and the GEMS mission over Asia. So it's geostationary, every hour providing data with a resolution of about 8 by 8 kilometers. The interesting thing is that it's on MTG sounder platform together with the infrared sounder, and the infrared sounder has also capabilities to measure, for example, CO or ozone from the thermal infrared. Then in the middle we have the METOP SG platform, so this is the follow-on METOP platforms. It will have a TROOTROPOMI-like instrument, but also a ESA instrument, so a thermal infrared instrument, an aerosol instrument, a MET image instrument, which is similar to VIRS. So that's quite a big platform that contributes in several ways to atmospheric composition monitoring. And then we have CO2M, which is the mission, the Copernicus mission for greenhouse gases. So it will measure methane, CO2, and NO2 with a resolution of about 2 by 2 kilometers. And there will be multiple platforms launched around 2026. So we will start with 2 and hopefully we'll add more of those platforms later. Then in the bottom, there are some candidate ones. There's the Tango mission that we are working on. This is a CubeSat mission consisting of 2 CubeSats measuring the greenhouse gases and NO2 with a resolution of 300 meters. We hope that we can develop this so we can launch it around 2026 as well. And then there's NitroSat, which is really targeted to reactive nitrogen, measuring ammonia and NO2 with a resolution of 500 meters. So really looking at specific emissions and fields. However, if it's selected, it will not be earlier than 2030. So now I would like to show you some examples of what we do with the one Sentinel that we currently have in orbit that is contributed to atmospheric composition. That's the TROOTROPOMI instrument. TROOTROPOMI is an instrument spectrometer measuring in the shortwave specific bands in the UV-Vis, in the near and the SWIR. It's launched in 2017, but the science data starts in 2018 in April. We measure a whole suite of gases as well as aerosol and cloud parameters. And we have a good spatial resolution of 3.5 by 5.5 kilometers. And it's because it's part of the Copernicus program, it's also a free and open data policy. So the TROOTROPOMI instrument, here you see a picture of it, was developed and built in the Netherlands together with ESA. It's quite a much larger instrument compared to what we have in OMI. OMI was really the instrument that started it all, and without it, could not be built, this TROOTROPOMI instrument. But it's way bigger because we wanted to have a much better spatial resolution and also, at the same time, much better signal-to-noise per ground pixel. It's about 200 kilograms. You can see here, get an idea of the dimension of it. And what it does in the end, it's measuring the radiances in the shortwave spectrum at specific bands. So here you see one example of a spectrum that was recorded in 2022. So this was on a cloud-free day in the Netherlands. You see we have the 4 spectrometers. They are all targeted to specific gases. So you see in the shorter part, you see the ozone absorption and the ozone absorption in the Huggins bands, and then we have the ring spectra, and we have NO2, and you can see all the gases. And in the shortwave infrared, the spectrum looks quite different because they have a lot of line absorptions from water vapor and methane. So this is just one spectrum I'm showing. We measure about 450 of those per second. And every day we record about 20 million of these spectra that we all have to analyze. So it's a really large data set that we are collecting with this instrument. Together with a consortium of institutes in Europe, we have developed a set of operational level 2 products. So these are also the products that you find on the Copernicus data hub. So we have products on ozone, NO2, CO, formaldehyde, methane, SO2, and aerosols and clouds and UV. On top of that, there's also some scientific products that we generate within another facility from ESA. That's for example, the glyoxal and the fluorescence of plants, etc., aerosol optical thickness. If you're interested in those, then we can always contact us to see if we can make these products also available to people. So what's very important about this, how we address it, is that we do a constant validation of these data products using ground-based data, and also that we are constantly doing algorithm evolution. So we try to make these products better and better going through the mission. So what took us some time, but what we finally finished in April, was a complete reprocessing of the data set. So this is now a data record of more than 5 years. We produced about 400 terabytes of level 1B data and about 100 terabytes of level 2 data. So it's a huge effort that we did there. And we did several improvements on the data products. For the level 1B, we improved the calibration quite a bit. And also, it's now consistent data records without jumps due to different versions of algorithms, etc. And same is true for the level 2 data, where it's really now a complete and consistent data record. So as I said, we do continuous validation. We have a system that automatically takes in all the data from the ground-based networks and then compares them automatically to our satellite data. So this is an example I just took this morning from our websites, which is a comparison between the NO2 measured here at NCAR using the Pandora instrument with the NO2 that we measure with TROOTROPOMI. And you can see it's quite recent, so the last day data was added to this a couple of days ago, and the comparison looks quite okay. So this is a kind of an operational system that we built to constantly evaluate the data that we put out. So during the 5 years that we had in the mission so far, we have seen some very interesting things happening in our atmosphere. This started off with, of course, with the Australian fires in 2019 and 2020, which had a huge impact on the southern hemisphere. I think these are the largest fires that we ever seen, causing large amount of smoke, but also CO to be transported all around the southern hemisphere. Then we had some interesting ozone hole seasons in 2020, with also over the Arctic, quite some low ozone. Of course, the TROOTROPOMI data were used a lot during the pandemic to highlight the changes in air quality due to the lockdowns. Then in 2020, we had the record concentrations in methane. And in 2022, we had the Honga-Tonga eruption, of course, a major event that affects our atmosphere. Looking more recent, of course, we have the Canadian fires here being very important in North America. So that's where we contribute with several of our data products. So I've shown here 3. So on the left panel, you have NO2, which is really, you see the high concentrations because it's so short-lived, only close to the sources, so close to the fires. In the middle, you have the UV aerosol index, so it's a kind of a smoke indicator, and it's really sensitive to absorbing aerosols. And on the right-hand side, you see CO, that is, of course, much longer lived, so you can see the transport of the plume actually far beyond the continent, so all over the northern hemisphere. We also are working on an algorithm development on the aerosol layer height. We have currently a version in the that's operationally produced, but we have now a version that we think is a whole lot better. So what it does is it computes the kind of the center of gravity of the aerosol layer, and it's especially kind of developed for these kind of smoke conditions. And this is something that I'm very interested to see if we can compare it with models, but also with measurements, how this is doing. So if you have data from other sources, I would be very interested to compare it to this new version of the product. One of the things that really struck us when we first looked at the TROOTROPOMI data were these plumes. So here I'm showing, this is over over Saudi Arabia, over the Gulf region. This is NO2. You see all these plumes. This is every day an image, and they transport the NO2 with the prevailing wind direction. And we were hoping to see this because also in models we have seen this, but I was not, of course, convinced that this was real because I'm not a modeler. I'd like to see the observations first. But really they are, models are quite capable of predicting these kind of transport in these plumes. And these plumes, they can be used to get information also about the emissions that are underlying the plumes. And I think this is a major field where I see a lot of active research now to convert these plumes into emissions, to derive emissions from the concentration data. There's a wide range of methods that's currently in development by various groups, and that goes all the way from simple mass balance methods to divergence method, but also inverse modeling, where in the inverse modeling you take a whole model, chemistry transport model, to calculate back what the emissions are. And it's applied not only to NO2, but also SO2, CO, and methane, are gases that we currently are working on. And on the right-hand side, you see in the top an example where in the top you see the concentrations, and in the bottom you see the emissions that were calculated from these concentrations, in this case using an inverse modeling approach. And this is really also important when you think again about the policy making, because these emissions is of course the thing that you can control, and that's what people are interested in, where you want to have the data about to see if reductions in emissions that are imposed, if they are really realized. This is an example of NO2 emissions from a power plant in the Netherlands. And this power plant was shut off at some point. And we could actually trace this very accurately in our emissions retrievals. So on the right-hand side, you see the emissions for this that we derived for this power plant. And you can see that we can derive this on a daily basis. So on a daily basis, we can update the emissions when we have new satellite data coming in. And you can see exactly where it was shut off. And the blue arrow shows where it was reported to be shut off. But as you can see from our satellite data, we found that it was actually shut off 2 days earlier than it was reported. So that's really a very nice example of how we can use these data and how we can use it in a very precise way and also a good example of ways to show that what we derive is actually happening. So other examples that we worked on regarding emissions is also in the oil and gas industry, from the oil and gas industry for the Permian Basin. Here in the US, the Permian Basin is of course a major region for oil and gas production, but also as a consequence, a major region for pollutants as well as for emissions of methane that have been studied by several groups for this region. We looked at it using the divergence method. We calculated the emissions of methane. On the left-hand side and right-hand side, you see the emissions of NOx that we also derived from our TROOTROPOMI data. And that's interesting because a lot of the NOx produced in the region is coming from the heavy machinery and the transport all around this the oil and gas industry. And that's why the majority of the features that you find, especially on the western part of the basin, are spatially correlating with what you find in the methane emissions. And also for the methane emissions, we calculated the emissions on the whole basin, and actually different methods that were applied to TROOTROPOMI data, they come to similar kind of conclusions for this basin. And we are actively now in a project where we want to compare the different methods that have been developed. And this is a region, of course, that is, as you can see in the top right, comprises of like thousands of facilities, and it will be very hard to reduce emissions here because it's so widespread. It's very much more difficult to control emissions for such a facility, for all these facilities, compared to when you have one big facility where it's much easier to find the leak and to repair it. Then we have also found other emissions for methane. So this is an example from our colleagues from Esron in the Netherlands. This is from Buenos Aires, and this is from landfills. On the top, you see the TROOTROPOMI methane. First, an mean concentration over 2 years of data. Then in the middle, top middle, you see one particular day where you can see the plume of TROOTROPOMI with the TROOTROPOMI resolution in the shortwave infrared. And on the right-hand side, you see it's wind rotated and then averaged again. So you see that we could see that there was an enhancement in methane over this region. But with TROOTROPOMI, you don't have the full spatial resolution to go into a city and to pinpoint exactly where these emissions are coming from. And that's where the GHG set comes in. So GHG set is a CubeSat missions that have a very high spatial resolution, and they are very sensitive to methane. That's where it's built for. And once with TROOTROPOMI we identified this region, we contacted the GHG people so that they pointed at this region once they passed over. And in the bottom you see 2 snapshots, 2 images for 2 days of GHG set. And with this spatial resolution, you can exactly pinpoint where these emissions are coming from. And you can actually exactly tell the local people, well, this is what we think is happening, and what you see is that it's coming from these landfills, and especially from the part that are not covered. So better management of these landfills can help reduce emissions for these regions quite a bit. So now I'd like to spend the last couple of minutes on some outlooks on our satellite data. And the first outlook is the improved spatial resolution. So here I'm showing a graph with on the Y and the X-axis the foreseen launch year, and on the Y-axis you have the spatial resolution. The Y-axis is an exponential, is a logarithmic scale. So there's quite a bit of variation in spatial scales here. But what you see overall is that when you go forward in time, you see that we are quite strongly improving on our spatial resolution. And this is actually quite important because with the higher spatial resolution of TROOTROPOMI, we made so much possible, especially regarding these plumes and these analysis of these plumes, and to better understand what's going on with the emissions. But in the future, we will have even higher spatial resolutions, starting, for example, with the CO2 emission with 2 by 2 kilometers, but also with smaller missions that are more targeted, but have a way higher spatial resolution. So that's the first outlook. We will have higher spatial resolution in the future. And then, well, the focus on emissions, I think I stressed it already in my talk. This is something that's very actively pursued at this moment by many groups, but it's especially also important because that is an important link between what we measure and what the policy makers want to know. They want to know, are emissions decreasing as we expect? So this is going to be an active field, I think, for many years, also because there are many missions with this higher spatial resolution that I talked about. And then the third outlook are these small satellites. So here I'm showing some examples of what we are planning to do at KNMI. So this is the Tango mission, there's a CubeSat mission. There will be many of those which are targeted missions. They will not have this global mapping facility. They will just fly over and point to certain regions and have an image that region with a very high spatial resolution. And there are many of these in development, both from the publicly funded. For example, Tango is funded through ESA, but also commercially, and this will really change, I think, also the landscape in remote sensing of the atmosphere. Because you will not have this one TROOTROPOMI mission. There will be the backbone missions, so the TROOTROPOMI follow-on missions. And on top of that, you will have all these zoom-in missions that target specific areas and can image with a very high spatial resolution. And I think in the coming years we have to find out how to work with that, and especially also how this contributes to our science that we do. So with that, I would like to thank you for your attention. Here are some links also to some websites that are related to TROOTROPOMI. I will be here this week and also next week. So if you have any question about what we do or ideas how to use our data, please come and see me. I'm really interested to work together with all of you. And I thank you for your attention.
Thank you, Pepijn. Got a question. Room. Can I reach?
Hey, thanks. That was an excellent talk. I got a question about the CubeSats, right? The last talk, or the last point here. What is the business model for these companies that fly the CubeSats? Do they sell the data, or how do they make money?
Yeah, so the idea is to sell data in the end. And
who buys the data? Is it
that
CAMS is going to buy the data, or?
That could be Copernicus, could be one of the customers, but could also be large companies that they have to monitor their own facilities, and of course they can do this with measurements on the ground, but they could also add a space component to it. And cities might be interested in doing this. Yeah. Okay. So I'm not the commercial guy, but this is what I hear from the companies.
Yeah, it's happening in other areas. I mean, in meteorology, that's happening also.
Yeah.
So thank you for the excellent talk. I want to make a connection with one of your slides that's showing the Pandora, and with your data. That I appreciate that's our life's work and from our colleagues here. So my question had to do with if TROOTROPOMI has any program to connect the low capacity region, that high pollution, low capacity region, with kind of offering some Pandora instruments to connect with the TROOTROPOMI measurement to local, potentially very high polluted region. I am asking because I just came back from Dhaka, Bangladesh. So with the day there, we see obviously with the day, the visibility just decreasing and everything. And the GEMS PI, the Korean GEMS PI specifically said that he thinks his satellite is underestimating all the emissions in the region. So do you have a program to potentially help identify how TROOTROPOMI is doing in this off-chart region?
We don't have that as part of the TROOTROPOMI project. So what we do is we take all data that's on the networks. But there are other programs that actually want to establish that. I know the WMO is also very active at this point because they see actually in many regions the network on the ground declining. So they want to stop that. And I know that from the Netherlands there will also be a program where we adopt certain countries to improve their network. And as you say, it's very important because we have very limited amount of data sets from Africa. There are some groups in Europe who do measurements in Africa and also do operational measurements in Africa with Max DOA's instruments, but these are very few data points that we have on the ground in these kind of countries. So yeah, I think that's really necessary. And I think also here in NCAR you have an Africa initiative where we hope to improve the situation there, but also to improve how people in those regions can make use of our satellite data.
Thanks, that was a great talk. Just to follow up from Laura's question, NASA are actually putting Pandoras in a lot of places in Africa and in other parts of the developing world where there's not very much ground-based capability at the moment. But I had a question. What's the follow-up from the Dutch election nitrogen question between the data shown by TROOTROPOMI and by Chris for the ammonia and NO2? What's the outcome of that debate?
Well, you know, I think as well as I do that policies making is a slow process, usually. So there's not at this moment a confirmed way forward, but it has to be because you know the situation now is something that's not. There has to be some change especially in the agricultural way of working, not only for biodiversity but also for climate change, because this intensive farming also has in the Netherlands quite significant contributions to the methane emissions. And as we, as a country, signed the Methane Pledge, I think the only way to reduce methane is to address the intensive farming in the end. So yeah, there's it's a hard, it's a difficult problem, but it's also a problem for ammonia that existed already for 30 years. So it's a time that there's some change there.
Okay, one more question.
Yeah, so I would like to know a little bit more about Sentinel-4 and 5, the data side. I know you're strongly involved. So what are the plans from Europe to do with the Sentinel-4 data? And they will also be assimilated in this Copernicus system. How far are they? Is there a plan for that? Or?
So yeah, that is indeed. So these Sentinels, they are really one of the main goals of them is to be assimilated in this in the CAMS in the CAMS system. So there's a plan for it from the start. Of course, it will take time to shake out some of the algorithmic and maybe instrumental things with Sentinel-4. But we think it will contribute quite a bit because it's an hourly data set, especially for NO2. It will, I think, contribute a lot. And for Sentinel-5, that is like a follow-on to TROOTROPOMI. So what they usually will do is they will start first evaluating the data, so not actively using it in their system. But when they're convinced that it's consistent with the rest of their observations in their system, they will start to assimilate those as well. And that's, of course, also interesting because then you have globally a point in the morning with because Sentinel-5 will be a morning orbit, and then a point in the afternoon with TROOTROPOMI. So yeah, it's really the plan to use these data in the data assimilation systems. Yeah.
Okay, one more question, actually two.
Thanks, Pepijn. Isoprene has been retrieved from CRIS data, and it's super important, obviously, in atmospheric chemistry. So are there any developments on the European side to make more of those measurements with the upcoming instruments?
The isoprene, yeah, my guess would be that CRIS is in a good position to measure isoprene because of it has the right spectral coverage and resolution, but also because it's flying in the afternoon orbit, so you expect to have much more isoprene compared to what you get in the morning hours when the METOP platforms pass by. So I don't think I've seen so far, but there could be YASI measurements of, yeah, there could be, but they're probably not as high in concentration as in the afternoon.
Not sure about that, but they are there.
Yeah, yeah. And the next YASI, so the next YASI on the METOP second generation will have a higher signal-to-noise ratio and a higher spectral resolution, but it will be the same spatial resolution.
Okay, one question from Betsy online. Excellent talk. Does your team have methods for validating the CubeSat data? Do we have data quality requirements to use the processed data from the commercial companies?
That's actually an interesting question, and we are currently finishing a proposal for ESA, where ESA wants us to evaluate some of the upcoming commercial data. These are data of methane, where they want to use our expertise to validate it, to compare it also with existing other data products. So yes, we are working on that. Of course, it's a different data set because it's not this mapping mode, but it's really a targeting mode. So we have to learn how to do it, but it's certainly a thing that we are involved in. Yes.
Thank you. One more question from the room.
Thank you. I was wondering, it was very clear to see the map of NO2 and ammonia in the Netherlands.
Yes.
But of course, we know that the emissions, they don't have borders. So I was wondering if the countries, like I think below is Belgium, next to it is Germany, do they have also the same? Does it continue like on the right, the ammonia, or no?
Yeah, that's a very good question because we are a small country, so we also, I can say we are a net exporter of nitrogen. But that are important regions as well. For example, you see here in the southwest, you see these increases of NO2. They actually come from Belgium. So the Port of Antwerp is very close to that. So that's where these high concentrations come from. And also, you know, in neighboring countries, they have similar kind of problems. So in Flanders, it's part of Belgium, close to the Netherlands. They have similar problems with nitrogen and discussions also in policy how to address that. And we also see these high ammonia, for example, in Germany on our eastern borders. So yeah, that's why in the end for a long time we address air quality issues also on the European scale always. So we have these air quality directives. They are all based on the European legislation. Yeah.
Okay. Thanks everybody for the lively discussion, and let's thank once more Pepijn for his talk.